My name is Kathleen Coleman, and today I'll be talking about Physics 2, Lab 3 about bar magnets. The purpose of this lab was to measure the distance dependence of the magnetic field due to a bar magnet and compare measurements to the distance dependence predicted by the Biot-Savart law. For this lab, you need to understand bar magnets and the fact that the magnetic field lines go from north to the south pole, and also the Biot-Savart law and the distance dependence of the magnetic field of a bar magnet. Also the superposition principle, which says that the net magnetic field at a point is equal to the individual magnetic fields at that point summed up, and had a linearized nonlinear data. And then the main results of my experiment were that n equals negative 2.8049 and mu mag equals 3.69 amperes times meter squared. For the on-axis component of this lab, you need to compensate for magnetic north by rotating your phone until the magnetometer says that the x component of the magnetic field is 0, and then you need to find the magnetometer chip in the phone, and then you need to take some measurements by sliding the phone along the meter stick until the x component of the magnetic field is equal to the given value, and record the distance at which that happens. For the off-axis component, you need to find d perp, and then record the value of the y component of the Earth's magnetic field there, and then find d. You add a second meter stick and move the phone up until it is at point d perp on the second meter stick, and then you determine the x, y, and z components of the net magnetic field at this location, and then you need to correct for Earth's magnetic field as well. In this experiment, I assumed that the bar magnet can be treated as a magnetic dipole, and that the only magnetic fields are from the Earth and the bar magnet. And I assumed that the system is the bar magnet and that the surroundings are everything else. Here are some given observations, and only the first and the fourth are true. So when the magnetometer is far away from the magnet, it does measure a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field does increase. Here is a look at my experimental data for this experiment, and you can see my linearized data on the graph there. Now we need to calculate n. So n is actually just going to be the slope of that linearized graph, which for me was negative 2.8049. Here we have the calculation of the magnetic dipole moment. So I began by calculating k, and then I used that k value as well as the magnitude of the magnetic field from my data, and I used those to find r, and then I used r and n to find the magnetic dipole moment, which ended up being 3.69 amperes times meter squared. Now I'm going to go through some code. So I defined mu mag as 3.69, that's the magnitude of the magnetic dipole moment, and then I defined a function called dipole B, which gives you the magnetic field given the magnetic dipole moment and also r, and then I scaled the arrows to make them fit and defined the distance as 0.25, and then I went ahead and set the observation locations of the different points on axis and perpendicular. It's just a bunch of code where I find the magnetic field at all of those points on axis and perpendicular, and then I also make arrows representing the magnetic field at those points. And here I find d given d perp, which is from my experimental data, and then I find the magnetic field at a point 45 degrees from the axis, and I draw an arrow for that. Here's the output of the code. So we have the orange arrows, which represent the magnetic field on axis, the cyan arrows, which represent the magnetic field perpendicular to the axis, and then the magenta arrow, which represents the magnetic field 45 degrees from the axis. I got a pretty different value for the magnitude of the magnetic field experimentally versus computationally. I think part of this is because I use a different value of r for each, plus there were other magnetic fields which we didn't account for. There was also probably some inconsistency with the angle of the phone and inaccuracy of the magnetometer. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your values have changed? I think that the values would have been completely different. However, I think you could theoretically isolate the magnet's magnetic field if you know the angle between the meter stick and Earth's magnetic north, but it would be much more complicated. And what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to be different? And I think the direction of the combination of the magnet's magnetic fields would be the same as the direction of just one magnet's magnetic field, but it would be much stronger.